All right, time for fun and games, right? Exponential and logarithmic models. It's always the fun stuff. Now, when we're looking at this, they want us to graph the data out. With monthly payments of this, we got this. Okay, graph the data in the table with X as the age and Y as dollars. Now, they want us to create an exponential function that models these premiums as a function of age. So grab your calculators, of course. Here we go. Time to have some fun with this. So reset as always. Stat, edit. Now, always be careful about what your domain is. If we're dealing with years and they say years after, make sure that you do that. Oh. So, continuing on here. They just want us to go on age, dollars, so we don't have to worry about changing anything. So it's going to be 30, 40, 45. Oh, did I mistype that? Yep. Well, it's always definitely a good thing to go back, double check all the data, make sure that you put it in there correctly, because it does. Oh, I haven't had a chance yet. So then over here, 3, 4, 8, 5, 8, 3. Here, just grab one. Because I assume by now everybody's got a graphing calculator. They're using the one on their computer, or they have one. Everybody got one? Good. So, data has been put in. Now we need the exponential function for this. So we're going to hit second. Not second. It's stat, calc. And if you go from the bottom up, 0, exp. So it's going to give you an exponential regression on this. So we hit graph, not graph, enter, sorry. Enter, and we end up with our exponential function. Just that simple. So there is a neat little thing that I have caught on to here. Where did I write that down? Ooh, there you go. Second whiteboard up there, it says copy regression equation to y equals. After the equation is found, what we can do is we hit the vars key. So vars, which is right next to program. So if we hit the vars key, then we go down to number 5, statistics, and then we hit over to EQ, and we should, and where it says reg EQ, press enter. If we go back into y equals now, darn it, didn't work. Something went off. Try that one more time. Vars 5 EQ. Just there it is. Gotcha. So you got to go to y equals first. You got to go to the y equals after the equation is found, then go, yeah. So I've got it listed on there, and now rather than trying to type it all, write it down, which you should still do, and type it out, you've got this. So now we can go to window. We'll set that at 30, max out at 80. Values go from 100 up to 5,000. Second, y equals, turn the stat plots on. And now when we hit graph, we'll have our plots there, and the equation will be transferred over right away. So we see that the equation fits fairly well. So there we go. We've got them both graphed on the same. So now, here's another situation where they want us to go through and graph things out. Now, setting up the graphs for this stuff isn't all that difficult to deal with. I mean, we've been doing that for quite a while. Again, pay attention to what they're talking about. Graph the data, x equal to the number of years after 1990. So that means you're going to be doing 8, 9, 10, 11, 12, so on and so forth down there. Okay? Find the exponential function. We go through the key press and do that. Graph the data in the exponential model on the same axis so that you can see what's going on here. And now we're going to go through and use that information to answer the questions. So this is what the data graphs out to be. And we're taking a look at, what's the estimated e-commerce sales for 2015. Well, 2015 is here. We go back up here, and it should be right around what? Now, because we're dealing with this in terms of just looking at the graph here, this is why the graphing calculator helps us out so darn much. We can put in the value, and it will spit it back out for us. Do the calculation for it. Not a big deal. Okay? But that's essentially what you're going to be redoing. Okay? Now, we take a look here at E. It says the recession in 2008 caused retail spending to slow down. Remove the last 3 data points and then do it again. And that's very easy to do. You take out those 3 data points, go back in, delete it out, put that equation in there. And the interesting thing is, if you want to, you could have kept the other equation in there, generated a new one, and seen the comparison of what those 3 data points did, and then answer questions from there. Now, I realize that, yes, you can put this into the spreadsheet. I do find a spreadsheet to be by far more cumbersome for answering questions. It's a lot easier to hang on to the information, manipulate, and change. It takes a little bit more to set up, but the data can still be done, and you can create it in the same exact way. Now, determining which one we should use for it. We've kind of talked about this in the past, about looking at the differences and what's going on here. So, what it says here is if we have percent change is constantly spaced for equally spaced inputs, okay, an exponential function will be fine. Now, here are the outputs. Here's some data. We got a 1, 2, 4, 8, 16, 32. Looks like they're going up by a multiple of something, right? Look at the differences. So the difference here is 1, then it's 2, then it's 4, then it's 8, then it's 16, then it's 32. And it's asking, what is the percentage change? Okay. Well, there's 100% change going between each one of the numbers. From 1 to 2, it's going up 100%. 2 to 4, going up 100%. 4 to 8, going up 100%. So if this pattern is there, an exponential function is going to work rather well. Now, you'll also notice that there's another way of looking at this. When you look at this, the outputs are doubling, right? 1, 2, 4, 8, 16. Sometimes it's easier to see it that way. Is it going through and approximately multiplying everything out? by a value. Is it doubling? Is it tripling? Now, it also means it could be cut in half as well. So you need to keep that in mind. Which leads us here into sales. Now it says, suppose a company develops a product that is released with great expectations and extensive advertising, but sales suffer because of bad word of mouth from dissatisfied customers. Okay. Let's see. Can we think of maybe, what's that wonderful phone that works as well as a heater? Huh? Oh, Samsung's. Right? Is that what you were saying with Samsung? I thought you were saying that. So you got that Samsung, what is it? Samsung, whatever. Yeah, whatever that wonderful Samsung one is that heats. Okay. It was released, great expectations. Everybody was looking forward to this thing. Sales suffers because of bad word of mouth. Okay. So the monthly sales data shows the percentage change. Okay. So month. Things are going down, isn't it? Okay. How much is it going down? That is the first thing we need to take a look at. So I look here. Here it dropped by 72. Here it dropped by 133, 105, 81, 64, 49, 39. Okay. Doesn't look like it's doing much of anything, does it? But take a look at the percent of change. Now this is where actually looking at the percentage, for those of you that aren't quite giving me your attention, is necessary. Okay. What's the percentage change? Well, 22%, 21%, 21 or 22.1, 21.9, 21.1. Are these values fairly stable? It's right around that 22%, isn't it? So, based on this information, is this a good thing? Now, for those of you that are wondering, how do I get from there to there? The percentage change? Okay. If you need to, go back, calculate out, and see where those percentages are coming from. Come on. Clear all that stuff out. How do I get from here to here? Well, let's see, that would be 608 divided by 780, right? So I got that. If I go and subtract that from 100, correction, subtract from 1, that would be the percentage I would want. I get a 22%. So if you need to go and check that out and see what it is, so divide it out, find, okay, it's dropped by 22%. Does that seem current all the way around? Now, this is where it would come in really handy to have a spreadsheet built for this. You put your outputs in there, you put your differences in there, and then you can automatically program the darn spreadsheet so that it goes and calculates out those percentages. Easy enough. Rather than trying to go and fumble through the data all the time. Just giving you a little information, little hint there on what would make life easier. So, because this is relatively stable, that means an exponential growth model, or in this case, decay model, would fit it best. So, all exponential models, again, just remember, are going to be in the form y is equal to a times b to the x. B is our growth. Just keep that in mind. Let's see, we got that. Inflation. We don't like inflation. Comparison of models. Now, this is where it gets kind of tricky. Which model should we use? Blow this up here a little bit more for you. So, looking at that data, which is the best one? Which one would you want to use, the exponential? Does the quadratic look like it's a really good fit? What about the power model? So when I look at this stuff here, yeah, the exponential looks like it's, for this, looks good. Although I look at the power model and it looks like it's good from, except for the last 2 data points. Okay. So a lot of this is, you got to look at it. Now that quadratic model where it's coming down, that really doesn't seem to do much of anything, but then again, it is closer up here on these. Okay. So it goes on here and it says, when fitting exponential functions to data using technology, it's important to know that problems arise if the input values are too large. For instance, when the input values like 2000, 2010, technology determined model may appear to be in the form of that, a function which certainly does not make sense for a model of data. Okay. At other times, when large inputs are used, your calculator or computer software may give you an error message because it can't even produce the equation. To avoid these problems, it's always a good idea to convert years after a number of years specified. So when we are using the data, and it says identify years after 1900 or after 1990, that reduces the size of the inputs. When the numbers go in and they're too large, it tends to create problems with those functions. Be very, 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 very aware of that. Now, we've talked about this idea of correlation coefficient. Little note down there. It says statistical measures of goodness of fit exist, but caution must be used in applying these measures. For example, the correlation coefficient R found for linear fits to data is different from the correlation or the coefficient of determination R squared found quadratic fits of data. Similar, but not the same idea. Okay. Logarithmic models. So we can go through and do pretty much the same thing with logarithmic models. I don't think that we had, they didn't replicate the same data. So let's try this one here. We're going to put in some we're going to put the data in and see what we can come up with for a logarithmic model here. So clear this out. And again, resetting the calculator is usually the quickest way of doing it. So I want to put the data in here. Should I put 2010 in here? Would it be better off using 2000 as my starting point and then putting it in as 10, 15, 20, 25, 30, 35, 40, 45, and 50? Would that be a better way of dealing with things? So we got percentage. We got 15.7. Okay, data's in. So now we need to have a logarithmic for this one. So you'll notice that they've got ln here. A lot of times that is what we're going to be using, is just ln makes life a little bit easier and quicker. When we go to the stat button and we go to calculate, go down. You'll notice that they have something called logistic. Stay away from that. Keep this thing in terms of a natural logarithm. That's why they have the ln there. So we want ln regression. So we press enter, enter. So we've got our equation in there. So now we can go to y equals, hit that there. Now we're going to hit bars. Go down to 5, go over to EQ, REG, pops in the entire thing. The nice thing about this is we don't have to round our values because honestly, do you want to put all those numbers in there? No. So by using this feature, we're able to go put the information in and keep it as accurate as we possibly can. So, second, y equals, stat plots on. Window. Well, what's our data? Well, our data went from up to what, 2000? We're using 2000, but we set it at 2010, and it goes up to what year? Don't do that. There it goes. So we can go from 0 to what? What's a good number? 60? 0 to, we were dealing with percents here. 0, should we put 100 in there? So we got 100%. Would that be a good thing? Maybe, but we're never going to get to 100%. What was the largest value that they gave us? Which was what? 34? I can't hear you. Oh, 34. So at 50 makes sense? Y minimum 0, maximum 50. Yeah, see what we got. There's our data. There's our function. Does it hit it fairly well? Does it line up? Sure. So if we had to go and answer ourselves some questions here, in what year does this model predict to be at 26.9%? Again, there's a couple ways we can do this. We can just hit the trace, and we can run through this and see if we can come up with y is equal to 26 point what? 26.9. So now if I put in 29, I end up with 26.9. Yeah. So what year? So in 2029, that's when it should hit 26.9%, right? Now I could have gone through and put in, could have gone to y equals, say that I want 26.9, enter, graph. Second calc, you could do 5. I could do an intersection of that one. Yep. Intersection of that one. Yep. Yep. And it goes through and tells me exactly at 28.9. So does that mean that I would have hit it in the year 2028? So what's the answer? Is it 2028 or is it 2029? Well, no. Did it say? What does it say? The percent reaches 27% at 2029. So did they round the information? Because we're using predictive functions here based on data that was given to us, the rounding, does that make sense? It does. So don't try and be very precise with this. So if I would have come back and say, well, no, we got a 28.9, so that means that somewhere in December of 2028 or 2028 is when it hits that. rounded. If we need to be more precise going down to the month, they'll state it. But generally speaking, this would be appropriate. So again, put the data in, see what you end up getting. You can use a spreadsheet. You can do these things with it. Now, just be careful with it when you're going through and trying to identify what's going on with this. Now, exponents, logarithms, and linear regressions. We know how to go through and do that. Okay? When you're going through and taking a look at the differences, that is kind of going to give you an idea of what it is you should be looking at. Okay? Now, if you take a look here and just want to read through this here for yourself. Now it says the third row in table 5 has logarithms. Base E of the numbers, Y value. Second row has rounded to 4 decimal, it's rounded to 4 decimal places. Okay? First differences are constant. Then you know that you've got something for linear. So using linear regression gives us that. We get this information. I realize it kind of sounds like I'm talking in a circle to you guys. And a lot of times it is simply look at the data, see what you've got. Once it's graphed out, that kind of gives you a better idea which one to go to. If you're still unsure as to which one you should be using, take a look at the differences. Other than that, a lot of this is simply you looking at it, you making a determination which models should be used and the reasons why you chose them. Okay? So I'm going to let you guys get to work on this stuff. Questions? Ask questions.